Hello class, hello class. Back again, chapter 15, lecture 2. Okay, we're going to continue on with the equilibrium constant, capital K. Capital K. All right. This is also known as the law of mass action. Okay, I'm leaving out a few details just because we're doing video camera, and I don't want to bore you to death, although I'm sure you're already bored. Oh, and that's my timer going off. Yep, let me reset it. The law of mass action. So we're going to consider a general case first and how to write out the equilibrium constant, right? So again, as usual, little letters are stoichiometric coefficients, big letters are chemical species. This is for reversible reactions, right? I want you to remember when you write out equilibrium constant, okay, products over reactants. Products over reactants. Memorize that. Writing the equilibrium constant for this is very simple. Take your capital K equals, again, products over constants. You're going to take the concentration of the product raised to its stoichiometric coefficient. So we're going to have this. Concentration of C raised to its stoichiometric coefficient, little c. Concentration of D raised to its stoichiometric coefficient, D. Divided by the reactants. Take the concentration of A raised to the little a. Concentration of B raised to the little b. Just like that. That's what you do to write out the equilibrium constant. Pretty straightforward. Again, products over reactants, okay? And technically, when we have molarity, we put a little c here, subscript c, indicating that we're using molarity. We'll see in a little bit here that you can use Kp also, pressure, partial pressures. We'll come to that in a moment though. So let me go back to our example earlier. Again, we had N2O4 goes to 2NO2 gas. Okay? I'm going to write out the equilibrium expression, constant expression for this, right? Kc equals, again, products over reactants. And look at your notes. That's what we had a moment ago, except I didn't have a little subscript C. Okay? Again, this will apply at equilibrium, right? At equilibrium only. Let's take a look at an example. Let's take a look at sample exercise 15.1. Let me make some room. Okay, sample exercise 15.1, page 616. Basically, write the equilibrium expression Kc for the following reactions. So pretty straightforward, right? So we're going to have A, we're going to have 2O2 gas, goes reversibly to 3O2 gas. Right? And I will let you, I'll write it out in a moment. But go ahead and write out Kc for that, right? Then we're going to have B. We're going to have 2 nitrogen monoxide gas plus CO2 gas is going to go reversibly to NOCl. 2 NOCl, that is, gas. And then we're gonna have one more. We'll take a look at C. Okay, so silver plus, go with plus 2 NH3 goes to NH32 plus, right? So write out, take a moment, stop the video, write out KC for these. All right, I'm assuming you've taken a moment, written it out, but let's go over it. Again, products over reactants. So we're gonna have KC, again, products over reactants, concentration of O2 raised to its stoichiometric coefficient divided by the concentration of the reactant, O2 raised to a stoichiometric coefficient. Pretty straightforward, right? What about this one? Again, products over reactants. Kc equals and concentration of NOCl, again, molarity, raised to a stoichiometric coefficient of 2, divided by molarity of the reactants raised to their stoichiometric coefficients. So we have nitrogen monoxide raised to the 2, right? And then we're going to have molarity of chlorine raised to the 1. There's your equilibrium expression. What about the last one? Again, products over reactants, products over reactants, products over reactants. Like I keep telling you, memorize that. We're going to have Kc is going to equal, again, our product. Molarity of, there's stoichiometric coefficient of 1, divided by concentration, molarity, of our reactants. Okay, again, I think that's pretty straightforward, right? Again, if you have questions, email me. Otherwise, we are going to go on to evaluating Kc, which is pretty straightforward. You simply plug in the concentrations at equilibrium. That's all there is. So evaluating Kc, again, you just plug in the numbers, okay? Whatever they might give you. We're going to use our same reaction we've been using. Okay, again, we wrote out Kc, right? Again, products over reactants, right? Molarity of NO2 raised to the 2 divided by concentration of molarity of N2O4 raised to its stoichiometric coefficient 1, right? Well, in your book, they give table 15.1 on page 616. They give a bunch of experiments that they ran where they vary the initial concentration of N2O4 and NO2. But no matter what, at equilibrium, the amounts of the reactants and the products always has to equal Kc, okay? It always has to equal Kc. I suggest you take a look at that table, right? So since we have different amounts of starting material, we end up with different amounts at equilibrium. But no matter what it is, you should end up with Kc being the same. Let's take a look. We'll take a look at experiment 1. Okay, for that one, they give the equilibrium concentration of N2O4 in molarity as 0.0172 molarity, okay? They give for, whoops, I got that backwards. That's N2O4, I'm messing up. Gotta be more careful. 0.00140 molarity, sorry. For NO2, they have 0.0172 molarity. So we're going to plug them into that expression, right? Whoops, don't want to brackets there. For equilibrium concentration of NO2 squared, right? Divided by equilibrium concentration of N2O4, right? Plug that into your calculator. Okay, I'm not going to use my crap calculator here to do that. Plug that into your calculator. Then you're going to set this equals 0.211. All right? Now, they have 4 different experiments there. Again, I suggest you take a look at that table. Every time they calculate it, they get 0.211, or really close, because of the little vagrancies of the experiment. But if the temperature is the same, you should get the same number, okay? 0.211. Now, note, I have no units on there, okay? We normally leave units off of Kc, okay? Kc, the equilibrium constant, does not have units. You leave them off, all right? Again, if you have any questions, I guess email me. You know, I don't know. But I'll write that down. Kc has no units, all right? Kc has no units. I hope you're all with me. Again, this is really weird lecturing to a camera. All right, let's go to equilibrium constants in terms of pressure, okay? So we're going to look at Kp, all right? It's the equilibrium constant in terms of pressure. Or partial pressure, actually. Basically, when you have partial pressures, you might remember, we could use those as concentrations. So that's why we can write Kp, right? Kp, it's very, very simple. If you have pressures instead of concentrations, you just use the partial pressures. It looks like this. We'll take a generic equation again. Reversible. Like thus, all right? And now we're going to write out Kp. So say these are in terms of partial pressures, right? So you use a subscript P, and all you do is write in the partial pressure. So you have partial pressure of capital C raised to the little c, stoichiometric coefficient, times the partial pressure of D raised to its stoichiometric coefficient, like thus. Products over reactants, that has not changed. And then we have the partial pressure of A raised to its stoichiometric coefficient, little a. And then we have the same thing, partial pressure of B raised to its stoichiometric coefficient B, if they're there, right? So this is actually exceedingly straightforward. Very similar to Kc. If these are given in terms of partial pressure, atmospheres, torr, whatever, you just use this instead, right? It'll usually tell you. Now, your book goes through a derivation so we can come up with an equation to go between these two. I'm not going to go through that derivation. You can look it out in your book. It's on page 617. I know you're all really interested in that. You're going to check it out. But I'm going to write it. So we can go between Kc and Kp using the ideal gas law, all right? And our equation for this is going to be, sorry, hold on one second here. We're going to have Kp, what did I do, is going to equal Kc times R, the gas constant, 0.08206 liters atmosphere mole, times the temperature in Kelvin, okay, in Kelvin, raised to the delta N. My timer's going off. I'll end here in a moment. Actually, yeah, I will end here in a moment. So again, R, 0.08206 liters, atmospheres, mole, Kelvin, temperature in Kelvin, okay, in Kelvin. And then what is delta N? Delta N is the difference in the moles of gas, which I have here, and I am blanking for some reason off the top of my head. Moles of products minus moles of reactant, like that. So moles of product minus moles of reactant, all right? And we're gonna end this video here, and I will be back, and we'll continue on.